Hi, welcome back. Now we're going to start talking about projectiles. Let's get to it. So, projectile motion. There's a very specific definition of this. Something is fired, thrown, shot, hurled, put near the Earth's surface. And when put, I'm talking like a shot put. Horizontal velocity is constant. That's because in the x direction there's no gravity acting. Gravity only acts in the y direction. And then vertical velocity is the one that's accelerated because of gravity. Gravity acts in the vertical direction. And we ignore air resistance. Projectile motion is a form of free fall. The only force acting on the object is gravity. We ignore air resistance. We will occasionally talk about the practical aspects of what happens when you throw a ball and there's air resistance, because you're going to throw the ball slightly different, accounting for air resistance, than you would if there was no air resistance. We won't calculate it though. The math is ugly. So, one-dimensional projectile. Projectile that moves in a vertical direction only. That's what we looked at when we were studying one-dimensional kinematics. You drop something, you throw it straight up. That's what one-dimensional projectile is. We only calculate the vertical motion. There is no horizontal component. Now, two-dimensional projectiles. It's a projectile that moves both horizontally and vertically, subject to the acceleration by gravity in the vertical direction. Some examples: throw a softball to somebody else. You fire a cannon horizontally off a cliff. You shoot water out of a hose. Those are all projectile motion type problems, and we ignore air resistance. We calculate our vertical and our horizontal motion independently of each other, with the exception of time. Time is a constant within both dimensions. So here's your multiple choice question. Now, the horizontal component of velocity is constant. It's not accelerated. It's not influenced by gravity. And it follows the equation x equals the initial velocity in the x direction times the time that it's flying for. That comes from the third equation or the first equation, with all of the initial information canceled out and no acceleration. So if we were to look at a picture of a projectile being shot from a cannon off of a cliff without there being any gravity, this is what it would look like. The ball would move horizontally at a constant speed. These are pictures of the cannonball taken at equal time intervals. So that's what you're looking at. Now, the vertical component of the velocity is accelerated by gravity. And again, the acceleration due to gravity is 9.8 meters per second squared down. These equations have been adjusted for assuming that gravity is negative, is in the negative direction. These are just our standard kinematic equations that have been rewritten in the y direction, and instead of acceleration, we've substituted a negative g for the acceleration to account for gravity being in the negative direction. I feel perfectly comfortable if you just use the kinematics equations as you have done so far. Now we're going to look at the horizontal and vertical motion together. You can see the horizontal motion is just as it was in the previous slide, and now we've added the vertical motion. And you can see that the ball is getting spaced further and further apart as it falls. Again, these are snapshots taken at equal time intervals. So the ball is going a further distance down during each time interval. Now here's just a little note to remind you, perpendicular components of motion are independent of each other. This was actually discovered by Galileo. And he's the person that did some of the initial work with two-dimensional kinematics, and he did a number of experiments and showed this to be the case. Now we're going to look at a particular class of projectiles, zero launch angle or horizontally launched projectiles. So the launch angle is the angle at which the projectile is launched. Big surprise there, I bet. And the launch angle determines what the trajectory of the projectile will be. And launch angles can range from negative 90 degrees, which is what happens when you're throwing something straight down, to a positive 90 degrees, throwing something straight up, and everything in between. Now, zero launch angle. This is our Canon picture again, but in this one, the ball's path along the trajectory has been sketched in. Basically, the X position of the ball was located at the same place as the Y position. So we see that the ball moves horizontally at a constant velocity, but vertically at an increasing velocity. Now I have a sample problem for you. Yes, water flowing over a waterfall is an example of projectile. We're assuming there's not air resistance and that the water leaves the cliff or the fall perfectly horizontal. So the Zambezi River in Africa, it's the Victoria Falls. The falls are about 108 meters high, and if the river is flowing horizontally at 3.6 meters per second just before going over the falls, what is the speed of the water when it hits the bottom? And we're going to assume that the water is in free fall as it drops. In other words, we're ignoring air resistance. Okay, let's first draw a picture that helps us visualize the problem. And I usually just draw it as a cliff and say that the water is going that way perfectly horizontal at 3.6 meters per second. Let me clean that up a little bit. And the falls are 108 meters high. And I'm going to just do a quick sketch of what I think the water is doing. It's following a parabola down. Okay. And sometimes I'm interested in how far it lands from the cliff. But in this, we're not asked anything about how far the water lands horizontally from the cliff. We're just asked for the speed, the magnitude of the velocity. Now, I'm going to write down the X information, the table of information for the X direction, and the table of information for the Y direction. A while ago, I mentioned that there are times when it makes a lot of sense to make positive down. This is one of them. So here we go. I'm going to say that that direction is positive and that direction is positive. It's a tool to help make this just a little bit easier. Okay, x0. I'm going to assume that it starts at 0. I don't care where it lands. The initial velocity in the horizontal direction is 3.6 meters per second. How fast is it going horizontally when it gets to the bottom? Well, if you said that it's going the same velocity in the horizontal direction, you would be absolutely correct. It would be 3.6 meters per second. And if there's no change in velocity, that would mean that the x component of the acceleration is equal to 0, and the time is something that we're looking for. We don't have enough information in this set of information. We don't have enough information to solve for the time. So we're going to have to look to the y direction and see if we have enough information there. The initial location is, I'm going to say that that is 0. The initial height is 0. The final height is 108 meters. The initial velocity in the y direction, well, it's all horizontal, which means that the vertical is 0. And the vertical component of the velocity when it gets to the bottom is something that we're very much interested in. And the acceleration in the y direction is 9.8 meters per second squared. Yes, it's supposed to be positive, and that's because of how I set up my coordinate axis as positive being down. And then the time is something that we need to know. Now, why do I need to know time? Well, I need to know time so I can find the velocity. Well, actually, do I need to know time? Do I have enough information? I don't need to know time. Mr. Miller, what were you thinking? I don't need to know time. I can solve for the vertical component of the velocity with the information that I have without needing time. So let's go ahead and do that. Which equation would I use? Well, let's see. I think that's the fourth one because it doesn't have time in it. Vy squared is equal to V0y squared plus 2a delta y. And we're looking for the final velocity, so we don't need to do any rearranging. So Vy is equal to the square root V0y squared, 0 squared, plus 2 times 9.8 times 108. And after you calculate all of that, that comes out to about 46.0 meters per second. Now this is the y component. We want the speed of the water. The speed of the water, or the speed, is the magnitude of the velocity. And the components are the final in the x direction and the final in the y direction. So the component or the magnitude of the velocity, we call that speed, is equal to the x component squared plus the y component squared. And if you recognize that as Mr. Pythagoras' theorem, you're absolutely right. Now I'm just going to substitute in 3.6 squared plus 46.0 squared, and that comes out to 46.15 meters per second. Okay, a lot of work goes into solving a problem like this because we have to work in 2 dimensions, and then we have to do the vector work. We have to compose the vector at the end. Next up is your free response question. Good luck. We'll see you next time.